Last week, we're in Module 4, and we left off with practical antenna systems and the most and easiest, in my opinion, antenna to build is a dipole. And we'll talk a little bit about what a dipole is. It's the simplest of the antennas. A dipole means two electrical parts. So it can be something as simple as two wires running horizontal from a connection point. And that was the first antenna that I built was a dipole. And you have to measure and determine the length and what frequency you're going to use it on. But they're very easy to construct. They're made from straight conductor wire, 1/2 wavelength long, with a feed point somewhere along the antenna, and that feed point's usually in the middle. So you have two equal lengths of wire coming out from the feed point of the antenna. Most are oriented horizontally, and particularly on lower frequency bands, radiate a horizontal polarized signal. They can be also installed vertically, sloping, or even drooping from a single support in the middle, and it's called an inverted V. So if you look at it, it's like if my fingers were the wires, an inverted V is you'd pull the connection point up on a pole or tree or whatever and run your wires out. And that's what an inverted V dipole would be. The radiation pattern is isolated in space and looks like a donut. All right, another type of antenna is a ground plane antenna. Most common type is 1/4 wavelength long with the feed point at the base. Acts like 1/2 of a dipole with the missing portion made up by the electrical mirror formed by the ground plane. And we'll look at some diagrams to give you an idea on this. It's made from sheet metal or screen wires called radials, a screen of wires called radials that extend out from the base. So this is talking about the ground plane. You've got your antenna coming up like this, and then these would be the radial wires going out from each point of the antenna. Extended length is 5/8 wave ground plane, focuses more energy toward the horizon, so it gives you a better range. To reduce the physical size of an antenna, it's often constructed with some of the radiating conductor wound into a coil or a separate inductor inserted in the antenna. It's called inductive loading. So that's going to be a question. And so remember inductive loading. All right, here's a couple examples of antennas. This first one here, now that's just because of the drawing. It's a dipole, and that would normally be running this way, but they've got it on the side of the drawing, I guess, to save space. This would be the connection point where your coax running from your radio would attach, and one wire or one conductor would be attached to this wire, and the other conductor from your radio would be attached here. This is a conductive ground plane. This would be the antenna going up vertically, and this would be some kind of electrical conductor, such as radio wires. If you look here, again, this is the antenna vertically, and these are wires that run out and provide the electrical image of the dipole. And then again, here's another vertical antenna with counterpoise radio wires. So all different frequencies would require different setups. Um, a ground plane, let me move my picture over here. A ground plane makes up an electrical mirror that creates an image of the missing half of the ground plane antenna. The result is an antenna that acts very much like a dipole. The ground plane can be made up of screen wires, often used at HF. You could literally take a window screen if it's metal, and you could put it at the base of the antenna to create the ground plane for the antenna, or a metal surface or wires running out. For VHF and UHF antennas mounted on masts, a counterpoise of a few wires serves the same purpose. I have a 2 meter antenna mounted out on the pole behind my house, and it's got these little radials, they're not very long, that run out for it, and they serve as the ground plane for my antenna as well.
Did you say a dipole is usually horizontal, or did I mishear
No,
that?
it's usually horizontal.
Okay.
It's usually just two wires of the same length, and they are horizontal to the uh, to the ground. So they run in this direction. If you can see me here. All right, antennas for handheld radios. I brought tonight, I remembered, this is a handheld radio. This is a 2 meter radio, and I've got a quarter wave antenna on it. Um, and I tell you, once you get into amateur radio, well, you'll get into these little handhelds. I can't tell you how many I own because I find one and I like it. My favorite, this is an Alinco brand. But my favorite right now is a BTEC UV Pro and radio. It's a little more expensive. This one, just to give you a cost, uh, is was $100 when I bought it. I don't know what it is now. My BTEC UV Pro that I bought, and it's out in my truck. I carry it in my truck. It was about $150. Now, do you have to go out and buy $100 radio? Nope. You can get on Amazon right now and order a Baofeng, and you'll hear people grumble and growl about Baofengs, but they're a good radio to start learning on. You can get one for $35, $40. So you don't have to go big when you first get into this hobby. You can go small. The more expensive the radio, usually it's more complicated. The UV Pro is one that, though, is very easy to program. You program it through your phone, and that's what I really like about it. The flexible antenna used with most handheld radios is called a rubber duck. The ground plane antenna is shortened by coiling the conductor inside a plastic coating. Well, I don't have a rubber duck on this. I have a fairly long wire that's on here. These are made by Signal Stuff, and they're the folks that do the exam tools that helps you get your exam, take your license test online. They wrote a program, the guy that did it. This one I've got on a connector, so it's very easy for me to disconnect from the radio. And so, uh, but the rubber duck antenna would be about that tall, and it'd be black, and it'd be a lot thicker. And it's in a plastic coating. It doesn't transmit or see as well as a full-size ground plane antenna. With this connector on this radio, I can take it off and I can connect it to an outside antenna. Uh, when you're in a car with a radio like this, it's not going to work very well because of the shielding that's uh, caused by the car. So you need an outside magnetic antenna, so I can quickly disconnect this and connect it to my magnetic antenna I have mounted outside my car, and it does quite well. For best performance, when you're using a transceiver, try to hold it as vertically as you can. If you're near a repeater, that's not as critical, but try to talk with it, holding it up straight, holding your antenna up straight like that. As I mentioned, they're not very effective inside vehicles, up to 20 times less effective than an external mobile antenna. So when you take a little handheld radio like that and you get inside your car and you try to key up and make a contact, it's not going to work. The car shields it and keeps the signal from going out. It's easy to connect handheld to full-sized antennas using standard RF connectors. A 5-watt handheld can easily reach 10 miles with a good antenna. So that's what I'm showing you here. Is it's very easy. I can take that antenna off and connect it to an external antenna real quick, such as a magnetic mount antenna that's on my truck. All right. Calculating antenna length for a dipole. To calculate the length of a resonant dipole, halfway length long, you take 468 divided by the frequency that you're going to be transmitting at. So back to our little chart here. Come back, come back. There we go. This is a little chart. And so let's say you're going to build a dipole on the 20-meter band. Well, you're going to have to be a general first. I don't know if you can see that. I should have put this on the slide. You want to try to go to the middle of the frequency. You know, for general, you go from, on 20 meters, you go from 14.225 to 14.350. So if you're building a dipole and you're in the general band and you have your general license, you want to build that dipole so it falls in the middle of that frequency. That way, as you choose a frequency to transmit on, your dipole antenna would work for 20 meters. So, for example, at 50.1 megahertz, that's in the 6-meter band. The dipole length is calculated at 468 divided by 450.1. And so you would need 9.3 feet of wire or 112 inches long. And it's in red, so that's a test question. But you'd need 9.33 feet on each side. It's a dipole, so think of 2 wires. You're going to need 2 wires, 9.33 feet or 112 inches long. The value of the constant used in the formula accounts for the effects that cause an antenna to act like it is a little longer electrically than it is physically. The actual resonant length is affected by the height above ground, its electrical properties, nearby conductive objects, and so on. So, so this is a good estimate. If you were building a 6-meter band dipole, probably if I come up with 112 inches in real life, I would make it probably 118 inches long for each side. That way I can trim it back. If you cut it too short and it's not resonant, the only way to fix it is to measure out some more wire and hopefully you cut it a little bit longer. So when I build an antenna, I always go longer, make it longer than what you calculate it to be, because if you cut it short, it's no good to you. You've just wasted that wire unless you can use it on a different wavelength. And that's what it says here. Make the dipole a few percent longer at first. Use 490 instead of 468. Then use an SWR meter or an antenna analyzer to determine the resonant frequency. Assuming the resonant frequency is too low because the dipole is too long, shorten it until the dipole is resonant at the desired frequency. Now, one thing we'll talk about SWR meters and antenna analyzers in your area where you are. Find a ham radio club that you could join, and get it with an experienced amateur radio operator that's willing to help you. And they're called Elmers. Like I'm your I'm your Elmer tonight because I'm wanting to help both of you get your license, and I'm trying to show you things. And the reason I say get with somebody in an amateur radio club, an SWR meter can cost a couple of $100. In my case, the one I bought was about $400. So not everybody can afford that, but I would be more than happy to help you build an antenna and measure the SWR on it with my meter and help you adjust it so that you get it right. Not everybody has to go out and buy an SWR meter, but find an Elmer in your local radio club that could help with you building an antenna. Now, calculating ground plane length, that's the radials. The length of a ground plane antenna is half that of the dipole and is often estimated as length in feet. So you take 234 divided by the frequency in meters. So, for example, at 146 megahertz, a quarter wave ground plane is 234 divided by 146 would be 1.6 feet. So the radials would be 19 and a quarter inches long. Length adjustments also apply, similar to the previous note about dipoles. You may have to adjust the length on your radials. Now, another type of antenna is called a directional antenna. And if you're as old as I am, you remember a directional antenna. It wasn't used for radio, but it was used outside for your television antenna. And you'd have to rotate that antenna and point it to the nearest transmitter to pick up channels. Simple dipoles, ground planes, and loops work well, but they have little gain. Radiation patterns don't have strongly preferred directions. Using a directional beam antenna, get the best reception in one direction. On VHF and UHF, if a direct signal path is blocked, a beam antenna can be used to aim the signal at a reflecting surface to bypass the obstruction. Now, we'll tell you that is a test question. And it's going to ask you how can you get a signal if the path is blocked and you use a beam antenna to reflect at reflecting surfaces to bypass the obstruction. Most widely used type of beam antennas are Yagis, and I've got pictures I'll show you here in just a second. Yagi beam antennas have more gain than omnidirectionals in their preferred direction. You can build a tape measure Yagi, and I'll show you a picture of it. You go to Harbor Freight, buy you a cheap tape measure, and you can build a 2-meter Yagi antenna to use in directional finding. Now, why would we want a directional antenna? Well, in our club, once or twice a year, we do what's called a fox hunt. And a fox hunt is nothing more as you take a radio transmitter and you hide that, and it's transmitting on a certain frequency. And the other members of the club start out looking for that transmitter. Normally, what we do is we hide one in a public place, such as a park here in Bowling Green. And then the guy, we say, all right, the fox, and that's what the hidden transmitter is called, is going to be transmitting starting at 10 a.m. on next Saturday. And we know the frequency. So everybody gets their handhelds and they hook up their Yagi antenna and they get out in different parts of the county and they start doing direction finding to find the fox. So it's kind of neat, but we'll go ahead. I'm getting off track here. The radiation pattern of a typical 3-element Yagi antenna with a driven element, a reflector, and a director shows that most of the antenna's energy is focused in one direction along the boom. So again, my finger is the boom. You would have three elements or 3 cross members. I'll just use 3 fingers here. One is the director, a driven element, and reflector. And I'll show you a picture of one here in just a second. Small amounts are radiated toward the side and back. This antenna also rejects noise and interference from side and back. The round pattern of the isotropic antenna and the figure 8 pattern of a dipole are included for reference. So here's the figure 8 of a dipole. Here is what a Yagi antenna would look like. All right. This is a dish antenna. It's operated on 10 gigahertz and is portable enough to be taken on contest outings. Horizontally polarized Yagis are often used for long-distance communication, results in lower ground lows when the wave reflects from or travels along the ground. As frequency increases, the size of the Yagi elements becomes smaller. It becomes more difficult to construct practical antennas. And this is showing you a 1 gigahertz dish antenna. Okay, now here is the tape measure antenna I was talking about. And it's nothing more than a piece of PVC pipe. And it's got a driven element. And how do I know what the driven element is? It's the element, this is the coax, and he's measuring right now the SWR on it. So he's got an SWR meter attached to it. And so you've got one part of the coax going to this part of the antenna, another piece of the coax going this way. So that's the driven element. The radio signal's going to come out of the antenna along this radial. The reflector helps reflect the signal back to this, and the director helps point the signal out. Now, this gentleman, he's a big Parks on the Air person. He's known by the call sign KB9BBR. If you would like to build this antenna, he's got a YouTube channel, and you could search for building tape measure Yagi beam antenna. And like I said, probably less than $20 because you've got clamps and T parts here. So less than $20, you could build a Yagi antenna. Back in the day when we didn't have cable or the internet, this is a Yagi antenna, and it was a television antenna. So here's your reflector. This is the driven element, and these are the directors. So your TV antenna would be connected here. The signal would go down into your television, and you would receive your show that way. Excuse me. Last week I forgot to bring any water back here, and I got a little parched. All right. Any questions at this point? All right, hearing none, we'll move on. Now, on to practice questions about this section. Which of the following describes a type of antenna loading? Electrically lengthening by inserting inductors in radiating elements, inserting a resistor in a radiating portion of an antenna to make it resonant. I'm going to tell you that's not the answer. Installing a spring in the base of a mobile vertical antenna to make it more flexible. You know, we used to have car radios or car antennas, and they'd have a big spring at the bottom. And so I'm going to tell you that's not the answer. Strengthening the radiating elements of a beam antenna to better resist wind damage. So what do you think it's going to be? It's going to be A, because you're inserting inductors or coils of wire into the radiating elements. And when you get into ham radio and you see commercial antennas, some of them will actually have a wire running out, and then there'll be a coil of wire at the end. I've got a antenna that's essentially a dipole. It's a vertical antenna. It's got a coil in it, and then it's got a radial that comes off to the side. I'll try to set that up. It's a portable antenna. I carry it in a little bag when I go do Parks on the Air. I'll try to set that up and get a picture of it for you and show it next week. Which of the following describes a simple dipole oriented parallel to the Earth's surface? A ground wave antenna, a horizontally polarized antenna, traveling wave antenna, that's a distractor, a vertically polarized antenna. So what we're looking for, a simple dipole oriented parallel. So a vertically polarized antenna is going to be this way, so it's not going to be parallel to the Earth's surface. Ground wave antenna, again, that's a vertical antenna. So the answer is going to be a horizontally polarized antenna. So the answer is going to be B. What is the disadvantage of short, flexible antennas supplied with both handheld radio transceivers compared to a full-size quarter wave antenna. It has low efficiency. It transmits only circularly polarized signals. It's mechanically fragile. All of these choices are correct. So I'm going to tell you, they're not mechanically fragile. I've even had like on this handheld, I've dropped it with the antenna and it lands on the antenna. It might bend it. It could break it, but it most often it's not that fragile. So we know that's not, and it transmits only circular polarized signals. That's a distractor. The real answer is that they have low efficiency. Question?
No, the button just keeps going.
Okay.
I'm not sure. I'm sorry.
Oh, that's fine. All right. Here's an example of a handheld with the rubber duck antenna on it. I found that on the internet, so I thought I'd put that on there. And I can tell by looking at it, it's a Baofeng. So that's about a 25 or 30, $40 radio. So it's nothing wrong with them. People say, oh, you don't want to do one of those, but uh, starting out, it's a good radio to get some practice with. So that's a Baofeng. So they have low efficiency when they use that rubber duck antenna. Which of the following increases the resonance frequency of a dipole antenna? So we're talking about the two wires again. How do we increase it? Lengthening it, inserting coils in series with radiating wires. So that one's wrong. Nope. Shortening it, adding capacitive loading to the ends of the radiating wires. So I'm going to tell you that this one's not correct. This one's not correct. B's not correct. So it's either going to be A or C. And if you remember a while ago when I was talking to you about doing a dipole, you always want to cut it longer and then you do what to it to make sure you get it resonant. You're going to shorten it. So the answer is going to be C, shortening to get it to the resonant frequency. Always go long. You can go long and make it short. You can't go short and make it long. It doesn't work because you can't cut the wire. If you cut the wire too short and you try to make it long, well, I'll just twist it together on the end. That don't work. So always go long with the wire, but then shorten it back to the frequency that you want. What is the disadvantage of using a handheld VHF transceiver with a flexible antenna inside a vehicle? Oh, we talked about that. Signal strength is reduced due to the shielding effect of the vehicle. The bandwidth of the antenna will decrease, increasing SWR. That's a distractor. The SWR might decrease, decreasing the signal strength. Again, distractor. D, all of these choices are correct.
A.
It's going to be A. Signal strength is reduced due to the shielding of the vehicle. That is correct. What is the approximate length in inches of a quarter wave vertical antenna for 146 megahertz? And we talked about that and it was in red. Is it 112? Is it 50 inches? Is it 19 inches? Or is it 12 inches?
We're going to go with A for 112.
A is correct. No, wait a minute. C. Well, let me get back up. I thought it was 112 too. It's saying C. I'm going to back up real quick. Let's go back here. I can't remember where it was.
It was, I think, calculating the ground plane.
Okay.
Yeah, at 146 megahertz.
All right. So it should be 19 and a quarter inches long. So it was C. All right. They tricked us. I was thinking of the other one, the 112. So it's 19 inches. And 146 is in the 2 meter band. 300 divided by 146 is approximately 2 meters, which is almost 80 inches. Quarter wave of that is 20 inches. So 19 is the closest answer. I was thinking of the other answer for the other question. What is the approximate length in inches of a half wavelength 6 meter dipole? And I think this is the one that we're looking for. And
Yes.
that's it is
Yes.
C
Yes.
112. See, I don't know it all. So sometimes I miss them too. And the easiest way to solve this problem is to remember that a meter is a little longer than a yard at approximately 39 inches. To calculate this, half of the 6 meter wavelength would be 3 meters. And to convert that to inches, multiply by 39 inches per meter. So 3 meters times 39 gives you 117 inches. Well, the closest one to that is 112. So, in which direction does a half wave dipole antenna radiate the strongest signal? Equally in all directions, off the ends of the antenna, in the direction of the feed line. So it's not going to, I'm going to tell you, it's not going to come down the feed line unless your SWR is way off. Broadside to the antenna. So when you're looking at a dipole, it's going to radiate the signal broadside to the wire. So it's going to be D. What is the advantage of a 5/8 wavelength whip antenna for VHF or UHF mobile service? It has more gain than a quarter wave antenna. It radiates at a very high angle. It eliminates distortion caused by reflected signals. It has 10 times the power gain of a quarter wavelength whip. It's going to be A. It has more than a quarter wavelength, more gain than a quarter wavelength antenna. What antenna polarization is normally used for long distance CW and single sideband contacts on VHF and UHF bands? It's not right-hand circular. It's not left-hand circular. Is it horizontal or is it vertical? Well, we're talking about continuous wave Morse code. Most of the time, that's going to be horizontal um, for long distance contacts. When using a directional antenna, we're called like a Yagi, how might your station be able to communicate with a distant repeater if buildings or obstructions are blocking the direct line of sight path? So we talked about that. You change from vertical to horizontal polarization. No. Try to find a path that reflects signals to the repeater. That's a strong contender. Try the long path or increase the antenna SWR, and the answer is going to be B. You try to find a path that reflects the signals to the repeater. What is a beam antenna? An antenna built from aluminum I-beams. An omnidirectional antenna invented by Clarence Beam? No. A is no. An antenna that concentrates signals in one direction. Think of a flashlight beam going out. So an antenna that reverses the phase of received signals. The answer is going to be C, an antenna that concentrates signals in one direction. And we've talked about that type of antenna. It's a Yagi antenna. Which of the following types of antennas offers the greatest gain? 5/8 wave vertical, isotropic, a J-pole, or Yagi? And we talked about it. The answer is going to be D, Yagi. All right, here's a chart, practical feed lines and associated equipment, common types of coax cable, has the loss in dB. RG6 has an impedance of 75 ohms. Loss per 100 foot is 1.4 decibels, and this is at 30 megahertz. and this is at 150 megahertz, it would be 33 decibels. RG8 is impedance of 50 ohms. Loss at 30 megahertz per 100 feet is 1.1. Loss per 100 feet at 150 megahertz, 2.5. RG8X, and I'm not going to read all these off to you, RG58. I will tell you in using this at my own home, I use the RG8X. It's very versatile. It's very manageable. You can carry it with you, coil it up. It's just a very good cable to use. It's not too expensive. When you get up to some of these others, they're going to be stiffer, harder to move, harder to feed through. Like if you're running your wire from your radio out to your antenna and you're going to have to go through the attic or something like that. Some of these others can be very difficult. Now, this is a very good LMR 400. It has a 50 ohm impedance per 100 feet. At 30 megahertz, it's only going to have 0.7 dB. And at 100 feet for the 150, it's only got 1.5. So it's a great cable, but it may be a little bit hard to manage. Coaxial cable, hams will commonly refer to that as just coax, and we saw that in table 4.1. Depends on the integrity of the outer jacket. So when you're using coax cable, you want to make sure that that outer jacket is protected. The biggest uh, um, contamination or the biggest hazard to amateur radio is getting moisture in your coax cable. It's the most common cause of failure in your coax. Prolonged exposure to the sunlight will cause the plastic in the jacket to grade. It will then crack, and then water gets in. And when it does, you might as well take that cable down and throw it away. If you've got a permanent install of an antenna at your house, you want to use the better cable. You might want to use LMR 400, but you want to make sure that the jacket on the coax is resistant to UV light. Otherwise, you'll be climbing up there and taking it down again. Coax should not be bent sharply. It can short circuit the conductor or the outer braid. And I meant to get a piece of coax and bring it tonight, but I didn't. But I'll bring some next week. Here are some types of connectors that you would use. The connector that you saw on my radio is a BNC type connector that's very easy to take on and off. You've got SMA, you've got phono connectors, SO239, which is connector like this. So there's all different kinds of connectors. BNC, that one is the one that's on my radio that I showed you. The type of connector to use depends on the signal frequency. UHF series of connectors are PL259 plugs and SO239 receptacles. This is a SO239 right here. They're the most widely used for HF equipment. UHF in this case does not mean ultra high frequency. It just means the HF bands. Above 400 megahertz, the type N connectors are used. And water and coaxial cable. You notice we mentioned this several times already. Water and coaxial cable degrades the effectiveness of the braided shield and it increases losses. In low loss air core or open cell foam coax, special techniques are required to prevent water absorption. So you may have a low loss air core cable in a repeater setup. Where that thing is operating 24 hours a day, 7 days a week, you will want to have low loss air core cable connecting the repeater to the antenna. If water gets in that, it can mess things up. All right, here's an example of a radio, and the cable is coming out of the back of the radio. It's going into this, what's called an SWR meter or watt meter. So your signal is, if you're transmitting, the signal is going to leave the radio. It's going to go out to the antenna. If you've got high SWR, that means your signal's not balanced with the antenna, so the signal could be reflected back to the radio. If you got high reflection back to the radio, your meter's going to read a high SWR. The SWR meter measures the power flowing toward the antenna and toward the transmitter, reflected or reverse. So when you have a high SWR, that's not good because your signal's not going out through the antenna, it's coming back to the radio. Most modern day radios, if you have a high SWR, will automatically power down or decrease the wattage of transmission to keep it from damaging the radio. That's why it's always good to have an SWR meter or some kind of meter to measure how your radio is working with your antenna. SWR meters measure SWR by placing them in series with the feed line, usually right at the output of the radio. I think that's a test question. Many radios include a built-in SWR meter. You can have, we'll have one on the radio, and you will see if it starts climbing, that means there's something wrong between the radio and the antenna, and you need to start checking your coax and your connections. A lot of times it can be just as simple as you didn't get your coax screwed in tightly to the radio or tightly to the antenna. Alternately, instead of an SWR meter, you can use a directional watt meter. It can be used to measure SWR, measuring power flowing toward the antenna and power reflected from the antenna by rotating a sensing element or turning switch. The most common folks use today would be an SWR meter. Antenna tuners. What do? Well, they take that impedance mismatch and they use it to put the SWR in line to keep it from being too high for the radio to operate properly. It doesn't eliminate that mismatch, but it can sort of filter it out and keep your radio so it will operate. It's connected to the output of the transmitter. It's adjusted until the SWR measured at the transmitter output is acceptably close to 1:1. Antenna system impedance has been matched to that of the transmitter output. Most tuners combine the function of an impedance matcher, directional watt meter, and antenna switch. Automatic tuners sense when SWI is high and will make the necessary adjustments. Here is some antenna analyzers. Both of these are made by Rig Expert. This is a little portable handheld. It looks like a stick. You can carry it with you. I carry one of these with me. It's rechargeable. And when I set up to say I'm doing a Parks on the Air activation, I will test my antenna to see what the SWR is before I get on and start transmitting. And I look at whatever frequency I've got my antenna set up. I have an antenna that does 20 and 40 meters. So a lot of times Parks on the Air, you use 20 meters. So you want to set it up to make sure that you're not getting a high SWR there. And then this is just another version. This one is expensive. This one is a little less expensive, but they both do about the same thing. They're used to measure an antenna system without using a transmitter whose signal might cause interference. So you connect this directly up to your coax and to your antenna. You don't have the radio in line with it. So that might be a test question as well. An antenna analyzer offers improved signal quality By identifying antenna issues like mismatch and cable faults, they help you optimize your antenna system for stronger signals and better communication range. They definitely make troubleshooting easy, quickly diagnose the antenna and cable problems, saving you time and frustration in resolving signal quality issues. Gives you confidence in your equipment, allows you to verify antenna performance, ensure your radio setup is operating at its peak efficiency. Now, some practice questions, and let me grab another sip of water here. Which of the following causes failure in coaxial cables? We mentioned this several times. Is it moisture contamination, solder flux contamination, rapid fluctuation in transmitter output power, or operation? A, that's correct. Moisture contamination. That's that. You want to make sure that your coax stays watertight and water resistant. So it's going to be A. Why should the outer jacket of a coaxial cable be resistant to ultraviolet light? Ultraviolet resistant jackets prevent harmonic radiation. Ultraviolet light can increase losses in the cable's jacket. Ultraviolet and RF signals can mix, causing interference. Ultraviolet light can damage the jacket and allow water to enter the cable.
D.
D. Again, water is your enemy when it gets into your cable. What is the advantage of air core coaxial cable? Say that fast 3 times. When compared to foam or solid dielectric cables, it has more loss per foot. It cannot be used with VHF and UHF antennas. It requires special techniques to prevent moisture in the cable. It cannot be used at below freezing temperatures.
C.
C. It requires special techniques to prevent moisture in the cable. And that is correct. Which of the following types of solder should not be used for radio and electronic applications? Now, I don't think we discussed this, but if you think about it, you should be able to get it. Would it be acid core solder, lead tin solder, rosin core solder, or tin copper solder? And acid is not good for electronic parts. So I'm going to tell you the answer to that one is A. And it's acid core solder is used to strip the oxidation layers off of a metal object to create a joint. It's used in most applications like plumbing where a watertight seal is needed. It's not suitable for electronics due to the corrosive effects. So, an easy way to remember is that acid eats away at metal, and that's not good for electronics where very thin metal contacts may be used. So, and there's a little tip. I got this, and we'll talk about this. This came off a Ham study, but acid core you would not want to use in electronic applications. What is the characteristic appearance of a cold tin solder joint? Now, we haven't talked about soldering, but if you get into ham radio, at some point you may build an antenna, and I will guarantee you it will require some soldering. Would it be dark black spots, a bright or shiny surface, a rough or lumpy surface, or excessive solder? And I'll just give you the answer. It's going to be C, rough and lumpy surface. So a cold tin lead solder joint, that's not a good joint. What you want anytime you're doing soldering, you want a bright or shiny surface. So after we get our license, we may continue to meet some, and I'll set up a camera and show you how to do some soldering and give you a few tips. I'm not a real good solderer. I don't solder very well, but we have a young lady in our club, and she is 11 years old, and she can solder very well. We went to the Huntsville Ham Fest, and one of the activities for the young radio operators, was to build a Morse code keyer. And she had to do a lot of soldering, and she was a lot better than me. So So a cold solder joint results when not all metal surfaces are properly fluxed, brought up to the needed temperature if the solder is disturbed during the plastic phase as it cools and hardens. When this happens, the surface of a solder joint will appear rough and lumpy instead of bright and shiny. Inspect every solder joint to ensure that the solder flows smoothly over all conductors being joined. Which of the following RF connector types is most suitable for frequencies above 4 megahertz? PL259, SO239, Type N, RS2213 or DB25. And it's, if you remember, we said the Type N connector, so it's B. Which of the following is true of PL259 type coax connectors? They are preferred for microwave operations. They are watertight. They are commonly used at HF and VHF frequencies. They are bayonet style type connectors. Well, they're going to be commonly used at HF and VHF frequencies. Which of the following is a source of loss in a coaxial feed line? Water intrusion into coaxial connectors, high SWR, multiple connectors in the line. All these choices are correct. So we know this is not correct. The answer is going to, well, wait a minute. Ha! They are correct. All of them are correct. Water intrusion, high SWR. Let me go back and read that question. Which of the following is a source of loss in coaxial feed lines? Well, water definitely is. High SWR is. I misread. Multiple connectors in the line. You cannot, when you're building a coax feed line, you want to have one connector on one end, one connector on the other, and you can't put a bunch in. If you do, it causes loss. So don't do as I say, do as the question says. What is the electrical difference between RG58 and RG213 cable? There's no significant, but RG58 has two shields. RG213 has less loss at a given frequency. RG58 can handle higher power levels, and it's going to be, it has less loss at a given frequency. Where should an RF power meter be installed? In the feed line between the transmitter and the antenna, at the power supply output, in parallel with the push-to-talk line and the antenna. That one makes no sense. In the power supply cable as close as possible to the radio. We're not measuring power supply like 120 volts. We're measuring radio frequency power. So it should be A in the line between the transmitter and the antenna, close to the transmitter. Which of the following is used to determine if an antenna is resonant at the desired operating frequency? A BTVM, an antenna analyzer, a Q meter, or a frequency counter? Anybody want to take a guess? Determine if an antenna is resonant. It's going to be B, the antenna analyzer. Which instrument can be used to determine SWR? Well, voltmeter determines voltage. Ohm meter determines resistance. Iambic pentameter is a a poetry term, I believe. A directional watt meter. So the answer is D. That I kind of laugh at that question every time I see it. But you know, voltmeter measures voltage, ohm meter measures resistance. So a directional watt meter or antenna analyzer would measure SWR. What is a major function of an antenna tuner, or sometimes called an antenna coupler? Remember, we're tuning the antenna to match the radio. It matches the antenna system impedance to the transceiver's output impedance. It helps the receiver automatically tune in weak stations. Nope. It allows an antenna to be used on both transmit and receive. That's kind of tricky. It automatically selects the proper antenna for the frequency band being used. And again, that's not correct. It's going to be A. It matches the antenna system impedance to the transceiver's output impedance. And that's the end of Module 4. We're halfway done. I'm going to stop the share for a minute, and I'm going to close this off. Do we have any questions? And I want to make sure. I think I'm still recording here.
I'm just going back through my notes from tonight. I got 3 pages, so it'll take me one moment. Dipoles, ground plane. All right, talked about the handheld antennas. I don't have any questions.
Okay, thank you. All right, now we're going to start with Module 5. And I want to make sure, can you see my screen with the young lady talking on the radio?
Yes.
Okay, good. Sometimes Zoom confuses me. So in this section, and we've got about 30 minutes, and I'm not going to rush things. If you have anytime you have a question, just raise your hand or come off mute and say, "Hey, Pat, I've got a question." So we're going to talk about modulation. We're going to talk about transmitters and receivers. This radio is both a transmitter and a receiver. I like Vanna White, have to hold it up here where you can kind of see it. It's not wanting to pick up, but it is a transmitter and a receiver. It receives and transmits signals. We're going to talk about digital communications, and I will tell you that digital communications involve using a computer connected to a radio, and you can do long distance communications with a computer and a radio. Excuse me. We're going to talk about power supplies and batteries. This little handheld radio has a built-in battery that you charge up. Some radios require a power supply, which is nothing more than a transformer, and it takes 120 volts and steps it down to 12 volt DC. So, as I've said in my other videos, ham radio is a hobby of 1,000 hobbies. There's something for everybody in ham radio. You just got to find what's interests you. All right, we're going to talk about modulation and bandwidth, and this is a basic radio station, and we've talked about this, I think, before. Here's a power supply. It's usually coming from your home. It feeds in 112 volt, and it supplies 12 volt DC to the transmitter and the receiver. And again, all this is in one box. In fact, not too long ago, a friend of mine, he had a radio from the 1970s, and it actually had a box that was a transmitter and another box that was a receiver, and it was connected but with cables. Now they're all in one box. So here's my transmitter and my receiver, and it's all in this one little compact unit. Then you have a switch that will switch it from receiving and or transmitting. Here's your antenna. This is your coaxial line running back to the radio. So combined, all this together, we call it a transceiver. And again, usually your power supply is taking 120 volt AC to 12 volt DC, and we call it a transceiver. Well, let me move that out of the way. What happens during radio communication? Well, when you're transmitting, you're sending a signal, and that signal may contain information such as voice, data, video, commands, etc., and it's converted to electronic form. The information in electronic form is added to a radio wave. The radio wave carrying the information is sent from one station antenna into space. So when I transmit on this little handheld, it's going to send my voice out over this antenna out into space. Probably not in the house because it's the house will block the radio communication. What happens during the radio communication? Well, if I'm transmitting on this, hopefully there's somebody out there listening with another radio and they're going to receive my signal. The radio wave carrying the information is intercepted by the receiving station's antenna. The receiver extracts the information from the received wave, and that information could be voice, it could be video, it could be data. Information is then presented to the user in a format that can be understood, such as sound, picture, words on a computer screen, response to a command, etc. What happens on radio communication continued, adding and extracting the information can be simple or complex. This makes ham radio fun, learning about how radios work. Don't get intimidated about all this. You will be required to only know the basics, but you can learn much more about the art and science of radio as you want. So there's lots of things. There's lots of digital communications out there. For instance, I'm familiar and have used FT8, and it requires a computer and a radio, and I'm pretty proficient at FT8. But there's lots of other digital communications out there that I've not taken time to learn yet. I'm waiting for some of my other fellow hams to learn it so I can go and say, hey, Tim, show me how you do that. So it makes it easier that way. When we add some information to a radio wave, the radio wave is the carrier, we modulate the wave. Turn the wave on and off. A simple way of using a radio wave is to turn it on and off, and that's Morse code. Speech or music, data, different modulation techniques vary different properties of the wave to add the information. Amplitude, AM, amplitude modulation, frequency, FM modulation, or phase modulation. A signal that doesn't carry any information is called unmodulated. Again, as you see things in red, that's probably going to be a test question. Recovering the information from a modulated signal is called demodulation. So if you're sending information over a wave, it's called a modulated wave. If you're retrieving that information, it's called a demodulation or demodulated. So here's continuous wave. Information can be added to a radio frequency signal by modulating the signal's amplitude. So I know you've seen the Westerns where they have the telegraph operators and they're pressing a button on a little telegraph key. Well, that's what this is right here. It's a telegraph key, and you're turning on and off with the key. And it's Morse code is a signal of dot and dashes. And you can see the difference in this. Here's an unmodulated RF signal. Here's one with a Morse code signal on it, and you can see the difference in that. The simplest type of modulation is continuous wave, turned on and off in a coded pattern. So when a lot of people were in ham radio will refer to Morse code as CW. Well, where do they get the CW from? It's from the wave, continuous wave. And it's simply turning that signal on and off. Morse code radio signals are called CW for that reason. Amplitude modulation. So you're changing the size of the AM signal. In amplitude modulation, the amplitude of the carrier wave is modified in step with waveform of the information, the tone shown here. Here's a modulated audio tone. This is an unmodulated radio frequency here, and you can see the information carried. The information is contained in the outline or envelope of the resulting signal. Recovering speech or music from the envelope of an AM signal is called detection. Composite signals, sidebands. Now, this we're looking at, here's the carrier wave. So this is we're looking at this kind of from the side. Here's a sideband. This is a voice sideband to that. Here's the other one. An actual AM signal is made up of three separate signals working together, a carrier and two sidebands. So this is your carrier wave, and this is your sideband. You got two sidebands. The carrier is a steady, unmodulated signal, has nothing on it. The upper sideband or USB signal is higher in frequency than the carrier. So here's the carrier looking at this chart. Which side is going to be the upper sideband? It says it's higher in frequency, so we're at 800 kilohertz. This is 800.3 to 803. So this is going to be the upper sideband. So if that's the upper sideband, this is going to be the lower sideband. The lower sideband or LSB signal is lower in frequency than the carrier. So here's your upper sideband. That's your lower sideband, and then this is the carrier. Single sideband. In an AM signal, the carrier doesn't carry any information. So when you're talking about an AM signal, the carrier wave doesn't carry any information. Each sideband contains a copy of the modulating signal. Only one sideband is needed to transmit the information. All of the single sideband signals power is concentrated on one sideband. So single sideband signals are effective for long distance and weak signal voice contacts because of the additional power. The upper sideband is used on VHF and UHF frequencies. Both USB and LSB are used on the medium frequencies or high frequency bands, and the approximate bandwidth of a typical single sideband voice signal is 3 kilohertz. So again, that's going to be a question. So what is the typical single sideband? What is the bandwidth of a typical single sideband? It's going to be 3 kilohertz. Frequency and phase modulation. Modes that vary the frequency of a signal to add speech or data information are called frequency modulation, or FM. The frequency of an FM signal varies with the amplitude of the modulating signal. Phase modulation varies a signal's phase instead of changing its frequency. In other words, it's very similar to FM. FM is the mode used by most VHF and UHF repeaters. This little radio is an FM transmitter. Because of the way FM receivers work, only one signal can be received at a time. This is called capture effect, and if multiple signals are present, only the strongest will be heard in the receiver. Again, that's going to be a test question. What is the capture effect? And it's when you have multiple signals coming into a receiver, but only the strongest one will be picked up by the receiver. So that's called the capture effect. Bandwidth of modulated signals. A signal can have both frequency and a strength or amplitude. Signals are spread out over a range of frequencies called bandwidth, and that's what this chart shows. It shows the different bandwidth for the different frequencies. And Joe, if you'll email me your address, mailing address, I'll mail you one of these cards. I've got tons of them, and I'll be glad to send you some if you'll send me your mailing address.
I'm going to do it right now. Thank you.
Okay.
Thank you, Pat.
You're welcome. You can communicate with single sideband over much longer ranges and in poorer conditions than with FM or AM, particularly on VHF and UHF bands. For even better range, extremely narrow CW signals are the easiest for a human operator to send and receive, particularly in noisy or fading conditions. So there's going to be a test question, I will tell you, that talks about CW, and it has an extremely narrow signal. So it doesn't require a lot. And CW or Morse code, you can literally transmit around the world quite easily. I'm not a Morse code. I don't have the dexterity or the ability to hear the dots and dashes. I'm not coordinated enough, I guess. But I know I have some ham radio buddies in our club that are Morse code experts, and they do a fantastic job. CW and single sideband are considered weak signal modes because they are more effective than FM at low signal strengths. If a single sideband signal can use either an upper or lower sideband, which one should you use? Ham radio has standardized on the following conventions. Below 10 megahertz, you use lower sideband. Above 10 megahertz, you use upper sideband, including all VHF and UHF bands. One exception, amateurs are required to use upper sideband on the 5 channels of the 60 meter uh, band. And I don't know if we can, I'll scan this, but right there, that is the 60 meter band. So you have to use the upper sideband on it. I know Brittany, you've got that you could look at, but I'll try to get it in the PowerPoint. Bandwidth of modulated signals. The approximate bandwidth of a typical single sideband voice signal is 3 kilohertz. And that's going to be an answer. So when you're talking about single sideband, it's going to be 3 kilohertz. So if you're within a radio frequency here, you wouldn't want to try to transmit at the beginning or the end of the band because that your single sideband is 3 kilohertz wide. And if you're right at the end of the band, you're going to be 3 kilohertz. Part of your radio signal would be out of band, and that you're not allowed to transmit out of band. The approximate bandwidth of VHF repeater FM voice signals is between 10 and 15 kilohertz. The approximate bandwidth of an AM fast scan TV transmission is about 6 megahertz. Again, all of these are in red, so there's probably going to be a question. So FM repeater, FM voice signal, 10 and 15 kilohertz. AM fast scan TV is about 6 megahertz. What is the approximate bandwidth required to transmit a CW signal? And it's 150 hertz. So a very narrow bandwidth, not megahertz or kilohertz. It's hertz. All right, practice questions. I keep looking at my clock. It's up over my left there. What is CW? A type of electromagnetic propagation, a digital mode used primarily on 2-meter FM, a technique for coil winding, another name for Morse code transmission.
D.
It's going to be D, Morse code. Continuous wave is just another name for Morse code. Which of the following is a form of amplitude modulation? Spread spectrum, packet radio, single sideband, phase shift keying. And which one of these have we talked about? It's going to be C, single sideband, SSB. It would help if they'd put that on that answer, but they don't. What type of modulation is commonly used for VHF packet radio transmissions? And we talked about this briefly. FM or frequency modulation or phase modulation, single sideband, amplitude modulation, or packet phase shift keying. And the answer is going to be A, FM or frequency modulation or phase modulation. Now, down here on these questions, I probably should point this out. This is out of Chapter 8, and it's in section A, and it's question number 2. And then this is the answer, and that tells you, I know, Brittany, you bought the book. This tells you the page number that this is discussed in the book. What type of modulation is commonly used for VHF and UHF voice repeaters? So we're talking about modulation, single sideband, phase shift keying, phase shift keying, FM modulation, or phase modulation. And the answer is going to be D. Which of the following is a disadvantage of FM compared to single sideband? Now, we talked about this when we talked about FM receiving. Voice quality is poor. Only one signal can be received at a time. FM signals are harder to tune. All these choices are correct, and we called it the capture effect. Do you remember which one that?
B.
Say again?
B.
B. One signal can be received at a time. So that's a disadvantage. If you got a bunch of signals, FM signals coming in at the same time, the strongest one will be the only one that will come through.
Way to go, Brittany. And it has to be, and it's going to capture the strongest signal out of those.
Yes, yes. So it's a, and
We got you muted, Pat.
somehow I must have touched the mute button on my microphone. Sorry about that.
We got you loud and clear.
All right, good, good. I tend to touch things I shouldn't touch. So there's a little button on the top of my microphone, and when I adjusted it, I must have hit it. Which type of voice mode is often used for long distance weak signal contacts on VHF and UHF bands? FM, DRM, we haven't even talked about, SSB, or phase modulation, and again, long distance weak signal. And if you remember, we said it was C, single sideband. That is correct. Which of the following types of signal has the narrowest bandwidth? Okay, we talked about this one. FM voice, single sideband voice, CW, or slow scan TV.
We're going to go with C, and that's 3. No, I'm sorry. It's 150 hertz is the bandwidth.
That is correct. It's so it's C, CW. Now, one thing I want to mention, remind you guys of, when you're studying these questions, don't remember the answer is C. You've got to remember the answer is CW, because when you take your test, these answers will be shuffled. So if you get this question on your test, CW may be answer A. So just be aware that the answers are shuffled when you actually take your test.
Okay.
Which sideband is normally used for 10 meter HF, VHF, and let me move something around over here. And UHF single sideband communications? Is it upper sideband, lower sideband, suppressed sideband? That's a distractor. We haven't talked about anything like that. Inverted sideband. So immediately you can eliminate C and D. You've got a choice between A and B. If you don't know it, you could guess. But if you remember, we talked about it being the upper sideband. So the answer is going to be A. What is the characteristic of a single sideband compared to FM? Single sideband signals are easier to tune in correctly. Single sideband signals are less susceptible to interference. They have a narrow bandwidth, and all these choices are correct. Most of the time, now we will get into some of the questions where a lot of them will have D, but it's the single sideband signals have a narrow bandwidth, so the answer is C. What is the approximate bandwidth of a typical single sideband voice signal? Now we're talking about the bandwidth. Is it 1 kilohertz, 3 kilohertz, 6 kilohertz, or 15 kilohertz? Do you remember?
For a single sideband, the bandwidth was 3 kilohertz.
That is correct. So the answer is B, 3 kilohertz. And sometimes on these questions, I'll tell you that we've talked about them. You may not remember where we talked about them, but you might just have to remember that it's 3 kilohertz. And in that one, that particular question, it is good to remember because when you get out in the field and you go to operating, the big reason you want to know that bandwidth is you don't want to get to the end of a band, say the 20-meter band. You don't want to start transmitting right at the beginning or the end of the 20-meter band because you'll be out of band because you've got that 3 kilohertz width that the signal transmits. So you want to remember that 3 kilohertz so you don't transmit out of band. What is the approximate bandwidth of a VHF repeater's FM voice signal? Is it less than 500 hertz, about 150 hertz, between 10 and 15 kilohertz, between 50 and 125 kilohertz? The answer on that one is C, between 10 and 15 kilohertz. What is the approximate bandwidth of an AM fast scan TV transmission? More than 10 megahertz, about 6 megahertz, about 3 megahertz, or about 1 megahertz? And we talked about that. It's going to be 6 megahertz, B. What is the approximate bandwidth required to transmit a CW signal? Is it 2.4 kilohertz, 150 hertz, 1000 hertz, or D, 15 kilohertz?
For a CW, that's
Yes,
150 hertz is
that
the
is
band.
correct. That's correct. It's a very narrow signal. So 150 hertz. All right, transmitters and receivers. Let's see. I'm trying to see where I am. When I'm looking over, I've got 3 monitors on my computer system. I'm going to try to run through this, see how far we get. Transmitters and receivers usually combined into one unit called a transceiver. They give you control of frequency and mode. Generalized categories are mobile, single band. In other words, they only transmit on one frequency. Dual band, they have 2 frequencies. This little handheld radio I have is a dual band. And then your base stations and some of your bigger radios could be all band and multi-mode. And then you've got your handheld or HT. So when you're using your radio and you're communicating, you could indicate I'm on an HT, so people would know that you're on a smaller radio. So that's the different types of radios that you can purchase. Single band radio is usually a 2-meter, and it's a good starter radio if you have some nets in your area. They operate on 13.8 volts DC. They would require an external power supply or a battery of some sort. Now, this says car battery. I would not recommend you buy a 2-meter radio and set it up in your house and use a car battery. And the reason I wouldn't recommend that is because a car battery can emit gases, and you don't want that. What you would want is like a lithium iron phosphate battery. They're about the same price as a car battery, but they're relatively safer than a car battery in your home. They require an external antenna and can be operated mobile or as a base station, limited to frequency modulation and usually either 2 meters or 70 centimeter bands. So my first radio was a Yaesu, I think 2980. It's a 2-meter radio. It's considered a mobile radio, but I have it set up in my shack as a base station. I have it connected to a power supply that I purchased that converts 120 volt AC to 13.8 volts DC. We just commonly, since it's 13.8 volts, we just usually say 12 volts because when you buy a battery, that's what you're going to ask for is a 12 volt battery. And it's only a 2 meter radio. It's not a 70 centimeter radio. And up to approximately 50 watts output, my radio on certain frequencies will put out 80 watts. And VHF, UHF, and FM. A dual band radio, same as a single band transceiver, but includes additional bands. Most common are the 2 meter and 70 centimeter bands, often include 6 meter, 1.25 meter, and 1.2 gigahertz bands. The most common you're going to see is the 2 meter, 70 centimeter bands. They might have separate antenna connections for each band or a single connection for dual band antenna. And there are approximately 50 watt output. And here's the typical frequencies. Multimode, nearly all HF rigs are multimode. VHF multimode operates on FM plus AM, single sideband, and CW modes. They're required for weak signal operation on VHF and UHF. More features add complexity and cost. So the more features you get on the radio, the more you're going to pay for it. More flexibility will allow you to explore new modes as you gain experience and increase license privileges. And there are ways like my HF radio that I bought cost me $1,200, but because I had good credit, I was able to buy that and pay it off over 12 months with no interest. So you can find there's a lot of companies out there that will let you pay it over time so you can own the better radios and everything. Multibands cover many bands, usually refers to the coverage of HF plus VHF and UHF. Also covers all modes, frequently 100 watts on HF. Some power limitations on higher bands, usually 25 to 50 watt. Their larger units have internal power supplies. Smaller units need an external power supply. The radio I have, it's a HF radio. I have to connect it to a battery, and it does have a built-in tuner. HTs, smaller handheld FM units, as you've seen, can be single band or dual band, limited power, 5 watts or less. I think this one's a 5-watt radio. Includes power, battery, and antenna in one package, often purchased as a starter rig, but low power limits range. Single, dual, and multi-band versions with increasing cost and complexity. Some can receive outside ham bands such as aircraft, commercial, FM broadcast, nor weather radio. This one can receive the weather radio. Very portable and self-contained, internal microphone and speaker, rubber duck antenna, battery powered, extra battery packs. Most of these radios, the battery pack just unclips from the back. You can buy extras for about $20 depending on the brand of the radio. This AA cell pack is useful in emergencies. I haven't seen many of those, but used to you could buy this holder that it would hold AA batteries, and you put them in there, and you could connect it to your handheld radio, and it would run the radio. Nowadays, it's just cheap to buy an extra battery for your radio. Drop-in charger. This radio that I have here has a drop-in charger where I drop it into the charger and it charges it. My new radio, the UB Pro that I bought, uses USB-C charging just like my phone. I just plug my USB-C cable into the battery and it charges it. Extended antenna, that's what I've got on this one. External microphone and speaker. You on the side of these radios, there's a jack that you can connect that to. I know you can't see that very well, but there we go. But there is a jack on the side of the radio where you can remove and plug in an external microphone and speaker. and then or a headset. And here's a comparison chart. There's not, I don't think there's a test question on it, but frequency agility, it's limited. You only got one band, dual band, medium, multi-mode is medium, multi-band is full, handheld limited. So it just gives you an idea of what each type of radio would be. Now, sample radios here. This is a Kenwood. It's a mobile unit, could also be a base unit. It's dual frequency. You can look at the screen there and see it's 2 meter and 70 centimeter. This is an HT. Some of these little HTs, I know my son has a Yaesu. I can't remember the model, but it was $400. So you can spend a lot of money on an HT. And then a multiband radio is something like this. Got lots of knobs and different frequencies, and looks like dual mode there, or dual VFOs. So I would say that's probably a $3,000 radio. Selecting band frequency and mode, two functions common to all radios. Control of frequency and mode. Amateurs can use many different modes. Most other radio services are limited to a single mode. For multi-band radios, begin by selecting the band, then select a frequency within the band called tuning, and use variable frequency or VFO or a keypad to directly enter frequencies. So a VFO knob is where you're turning a knob to select a frequency, or you can use the keypad on either on the radio or on the microphone to key in. And then memory channels are used to store frequencies and modes for later recall. Quickly tuned frequently used frequencies. And for multimode radios, you select the mode, such as single sideband, AM, FM, or data. Now, it's 8:04, and I've gone over. I try to limit this to an hour and a half so that I don't overload everybody. So is it okay if we stop here and we'll pick up the transmitter functions next week, and then we'll do the practice questions? Is that okay with everybody?
Sounds fine with me.
Yes, that's fine with me.
Okay, we'll stop here. We'll be back here next week at 6:30 Central Time, and we'll pick up with transmitter functions, and then we'll do the practice questions. We are now done with chapter. Like if you look at the test questions, we're done with. Give me just a second here. Let me see if I can get out of this. Okay. I'm going to stop sharing for just a second. I want to give you a brief, let me bring up, I'm going to show you a different study website. All right. And let me go back. Too many buttons to push. All right, I'm on the hamstudy.org website here. And let's see, and I'm already logged in. You can see my name here. We're going to go to the technician, and we're going to go to the study mode. And if you'll notice up here, it's bringing up all the questions. But we have completed section 5 of the technician questions. And you can go through here and you can study these questions and answer them. And so, for example, which term describes the rate at which electrical energy is used? And maybe I know that one. I'm going to try power, and it is correct. If I didn't know it, I could say I don't know, or I can click up here, and it's going to describe and tell you the answer. And So then you go to the next question. And as you're answering these questions, it shows you the percent aptitude and how many of the questions you have seen. So I've seen 96% of the Section 5 questions, but my aptitude is not up where it should be. And so I need to have it up to about 87 to 90% before I take the test. And that's only on Section 5. What you want to do as you're studying, you want to go to all questions. And then when you get that aptitude up to 97% as you study all these questions, then you're ready to take the test. But for now, you can go through and do Section 5, and I believe Section 6 was the other one that we covered. Yes. So Section 5 and Section 6, you can go through and get your aptitude up to what you need it to be for the technician license. And so I would encourage you, your homework is to go to hamstudy.org, create you a free account. It costs no money for that, and begin studying section T6 and T5 because we've covered all that in the videos. Any questions on that?
Nope.
Okay. Well, if not, we'll go ahead and we'll stop the session here. Thank you both for your participation. It just thrills me to death that I'm able to present this. And thank you all for being here tonight.
Thank you very much for being our, what was it, Elmer?
Elmer, yes, you're Elmer. So,
Thank you very much. I appreciate it.
all right, we'll have this up on YouTube in case you want to go back and watch it. So, you
I
all
will.
have a good night.
You too.
You as well. Good
All
night,
right.
everybody.
All right,
All right.
good night.